So now we are going to discuss about the measuring instruments. So measuring instruments means up to now whatever we discussed like EMF or the resistance or the potential difference. So all those values for measuring all those values we need some devices. So that now we are going to discuss about those devices, right? So in this the basic one we know about this galvanometer. So the galvanometer is a basic instrument and which has many applications, like it can be converted into ammeter and it can be converted into voltmeter. And so now see this galvanometer is basically used to find the direction of the current, and when you are using for the direction of the current, it resistance, whatever the resistance it is there, it doesn't matter. And if it is using to measure the current, when current is, we can also measure the current here, so then its resistance will plays a role there. And so basically we can define that galvanometer as a device used to measure the small currents and also used to detect the direction of the current. And small current means here you can observe this, we are finding of order microamperes. Generally the current order measured by this galvanometer will be of that range, microamperes range. And so now actually the working of galvanometer is also there for us, and that means how this needle will deflects and when the current is flowing, how it measures the current. And so that working of the galvanometer we will discuss later in electromagnetism. So in electromagnetism, it works on the principle of the torque acting on the coil in magnetic field. So we will discuss about the working, how it deflects, and later we will discuss that. And so now simply if G is the internal resistance of the galvanometer, so then G we already used it as a resistance of the galvanometer in Weierstrass bridge when we are discussing about that Weierstrass bridge. And so now this Ig is said to be the maximum deflection current, and so our maximum current that can pass through the galvanometer here. And so that means if maximum deflection means here this needle will deflect until the maximum value here. Then when this current Ig is passing through this, so that is nothing but our maximum deflection current here, right? And next here we can say here we need to note this one more definition here. The definition is nothing but like current sensitivity. The current sensitivity of the galvanometer is defined as deflection per unit current, theta by I. And so now here this current passing, this deflection produced here is actually passing through is directly proportional to the current passing through that. If more current is passing through that, then automatically more deflection you will get. And so now this current sensitivity is defined as deflection per unit current. So you will get the units like divisions per ampere. This generally the unit will be number of divisions per ampere, or it may be microampere or milliampere, they may mention in the different units. So generally it is of order microampere, so divisions per microamperes here generally. So general SI unit I am writing here, the divisions per ampere I am writing here. So that means now that is nothing but its meaning is, for if suppose 1 ampere is current is flowing here, how much division is how much divisions or how much deflection is produced in this. So that is nothing but our current sensitivity meaning here, right? And so next let us say about this reciprocal of this current sensitivity is nothing but we called figure of merit. So then this is figure of merit is nothing but the reciprocal of this value. So here we are writing this as theta by I, and here we write this as I by theta. So here current per divisions we need to write here. That means ampere per divisions we need to write here. So then that is figure of merit. And again more about this current sensitivity and figure of merit we will discuss when we are discussing about this working of the galvanometer, right? And so now here just learn the definitions here. Current sensitivity is deflection per unit current, and this current passing through this galvanometer is directly proportional to the deflection produced in this galvanometer is directly proportional to the current passing through that, right? And so now this figure of merit is the reciprocal of this. And so next here let us see about this ammeter. So ammeter is a current measuring instruments. The current measuring instruments is called ammeter. So that means now by using this galvanometer we are saying that we measure very small current here, right? And so whereas this ammeter we can measure the any range of current. That means for different ranges we use the different types of different ammeters having the different ranges there. And so now this ammeter is always connected in series with the circuit. Wherever you are connecting, suppose along a particular path here, for example, if you want to find the current passing through this path here, current passing through this path here, and so that then we need to find this, we need to connect this ammeter here, and similarly if you want to find the current passing here, then we need to connect an ammeter here. So it is always connected in series with the circuit where we want to find the current, right? And the resistance of this ammeter should be as low as possible. So here we are connecting this resistance in series. So if it is having more resistance, like suppose say for example this circuit I am taking here, 1 ohm and 3 ohms is there. So total resistance in the circuit is 4 ohms only, right? If this ammeter is having some 10 ohms, then total resistance in that circuit will become 14 ohms, which is much greater than that of this given resistance there, right? And so that if the ammeter is having that more resistance, then automatically effective resistance in the circuit will changes by large amount. And so automatically when current is, that means resistance is increasing by large amount, current passing through that will decrease. And so that means it affects the total current passing through the circuit there, if it is having that high resistance. And so to avoid that, it should possess the low resistance. So as much low as possible. And we consider this resistance of an ideal ammeter is 0. Resistance of ideal ammeter is 0. So practically if you are using this ammeter, it should possess a low resistance there. And so now here I am giving this a simple problems basing on this ammeter here. And here you can observe that no information is given about the resistance of this ammeter, how much resistance is present here. So that means in such a case you need to consider that as an ideal ammeter. If any resistance is there here, they will mention that resistance of this ammeter, then you should include that resistance there, right? And so that here no resistance is given means we need to consider it as an ideal. And so now here in this circuit they are asking the reading of this ammeter. So reading of ammeter means then it is nothing but it is connected in series with the battery. So it is nothing but total current passing through this battery we need to find here, right? And so now we can observe that this 3 ohm resistor, 3 ohm resistor and this 3 ohm resistor are in parallel. You can connect like this. That means this 3 ohm also we are connecting below here. There is no difference in that circuit. So then all these 3 are in parallel. The effective resistance of these 3 will be 1 ohm. You will get 3 by 3. And now this 1 ohm is in series with this 3 ohms here. This 3 ohms. And so total resistance will be 4. When total resistance is 4, then current we can write as V by R, so which is 3 amperes. So that is the current passing through this battery, which is nothing but the reading of this ammeter, right? And so next let us see one more such a problem here. The current I coming from the battery and the reading of the ammeter reading. So that means in the similar circuit they are asking the current passing through the battery and here ammeter is connected here. So then the reading here they are asking. So this is also similar to that of our previous problem. There just that 3 ohms are given and here just 4 ohms are given there, right? So I am directly writing that. We can draw this circuit like suppose here this resistance is there here and this is the cell. So first I am finding the total current here, right? And so now this 4 ohms is there and here effective resistance of these 3, right? This 3 ohm, 4 ohms and this 4 ohms and 4 ohms, all those are in parallel. So I can write this as 4 by 3 ohm. Now this 4 by 3 is in series with this 4 ohms. Therefore we can write this R effective value is equal to 4 by 3 plus 4. And so that it is 16 by 3 ohms, right? And therefore this potential difference is 3 volts and therefore this current we can write this as current I is equal to V by R effective. So it is 2 by 16 by 3. So which is nothing but 3 by 8 amperes. So that means current passing from this battery will be 3 by 8 amperes. Now when this 3 by 8 amperes is reaching this point here, you can observe that it has to divide that into 3 parts. Some current should flow like this and some current should flow like this, and again it will divide further here. So like this you should divide here. That means here from this you can say this circuit you can convert similar to this, that 4 ohms also you can connect like this. As all the resistors are same here, you can say this current will divide equally. That means this current we can write this as 1 by 8 amperes. And so here this is 2 by 8 amperes and again this 2 by 8 amperes will divide here. This current is 1 by 8 amperes and this current is 1 by 8 amperes here, right? So that is the current passing here. Now the reading, this total current is nothing but 3 by 8 and the reading of this ammeter is 1 by 8. So this will be the correct answer for that. So like that we need to solve in case of ideal ammeters, that just we need to find the current in the branches. So then that is nothing but the reading of this particular ammeter which is connected in that path there, right? And so now here generally if you are taking the practical ammeter, so practical ammeter means definitely it possesses some resistance there. So then in such a cases the reading of this practical ammeter is always less than the actual reading. So for example if you are taking this circuit here, as I said, if this resistance is, that means our resistance of this ammeter is 0, we are getting some 3 amperes current here, right? Now here suppose I am assuming some resistance is there for this. I am taking some let us say I am taking some 2 amperes 2 ohm resistance is there for this ammeter. This is an assumption, we are assuming that. Now let us see the total current here. The total current is nothing but 12 by total resistance. This 2 ohms plus 1 ohm plus this is 3 ohms. And so total 6 ohms you will get here. Total resistance. And so now this is nothing but you will get this current as 2 amperes. So if this ammeter is having 0 resistance, that means that is the ideal or actual current flowing through that circuit, we are getting this 3. But if this resistance is, if the ammeter is having some resistance, that means if you are taking that as a practical resistance, then we are getting this current as 2 amperes. So definitely what we can conclude here is, if the ammeter is having some resistance, that means practical ammeter if you are taking, the reading of ammeter is always less than the actual current, we can say here. And so now this is the simple circuit we are taking here. Suppose in this circuit if you want to find this current, then actually the current should be equal to, the actual current in this circuit should be equal to E by R. Now we are connecting an ammeter in series with it. Now suppose this ammeter is possessing some resistance which we are representing with the A here. This A we are taking as a resistance of this ammeter, right? And so now that resistance of the ammeter here they are representing with the G into S by G plus S. About this we will discuss later. Later now we will discuss after this introduction of ammeter and voltmeter. So let it be A, some resistance, whatever it may be, some resistance A is there here. Now in this circuit, after connecting this ammeter, the current passing through this is I dash is equal to now E by total resistance we need to write, which is nothing but R plus A. Now here you can observe that initial current is E by R, now it is E by R plus A. So here this denominator is increasing, from this we can say that this current will decrease here. So I dash will be less than this I we are writing here, right? And so that, and we can also conclude that this I dash is equal to I only when this A is equal to 0. That means if it is having this no resistance, that means ideal case, then only it gives it measures the accurate values there. And so now here the percentage error in the measurement we are calculating here. The percentage error is nothing but I minus I dash by I into 100. So now this I is nothing but we are taking like E by R and minus E by R plus A by E by R. So that E we are cancelling there. And if you simplify this, then you will get this expression here. The percentage error in the reading of this ammeter will be equal to A by R plus A into 100 we can write there, right? So that is in case of percentage error in case of practical ammeter. So you should remember that practical ammeter will always reach the less than the actual current there, right? And so now let us come to the voltmeter. So you know voltmeter is a device used to measure the potential difference between any 2 points in the circuit. So generally to find the potential difference between 2 points we use the voltmeter, right? And so now here another thing you need to remember here is it is always connected in parallel. Ammeter is always connected in series, voltmeter is always connected in parallel. Between which points you need to measure the potential difference, between those points you need to connect it in parallel. So and the resistance of this voltmeter should be as high as possible. So that means it should be having the larger resistance there. If it is having larger resistance, then it will be readings will be more accurate. Now the resistance of ideal voltmeter should be infinity. That means the voltmeter should not draw any current from the main circuit. If it is drawing current from the main circuit, then automatically the reading will decrease there. So for example here, let us take this example here. Here for example, if you want to measure the potential difference across this. So if you want to measure the potential difference across this circuit, now for this we are connecting some resistance here, right? That means voltmeter we are connecting here. To measure this potential difference across this, we are connecting this voltmeter. If this resistance of this voltmeter is infinite, then no current flows through this voltmeter. Whatever the total current flowing here, for example, here let us take this current 3 amperes is flowing, here there is no resistance. And so then 3 amperes is flowing here. And so then actually here this voltage should be 3 volts, right? Then IR value. Then if it is having this infinite resistance, then only it reads this IR value as 3 volts. But if it is having some finite resistance, when it is having infinite resistance, what will happen is, here whatever the current flowing here, the total current will flow like this only. That 3 amperes will flow along this resistance only. No current flows through this voltmeter because here infinite resistance is there. Infinite resistance is nothing but like open circuit. That is in case of ideal voltmeter. But practically what will happen is, it will possess some resistance, high resistance, but it is not infinite. So when it is not infinite, then automatically some current will flow here. That means like suppose out of this 3 amperes, 1 ampere current is flowing here, then only 2 ampere current will flow here, right? And so then the reading of this potential difference across this resistance will become, instead of this 3 volts, now it will become 2 volts. So that means now again the reading of this voltmeter will be less than the actual value. The reading will changes here. So because of this reason, the voltmeter should not, that means it should possess a very high resistance. That means practically, that means ideally we say that it is infinite. Practically it should possess as high as possible. And so that is the reason why it should possess a high resistance here. Got it? So the resistance of this ideal voltmeter should be infinity. Practically it should have the high resistance. Now let us take a simple circuit here. This in this circuit they are asking the readings of the voltmeter and ammeter, and here again you can observe that no resistance is given either for this ammeter or for the voltmeter. Then you can treat them as a ideal voltmeter and ideal ammeter. Then simply you can consider that these two are in. Now this voltmeter is connected across this 100 ohms. So you can observe this, it is connected in parallel across this. That means now this voltmeter will measure the potential difference across this 100 ohms only, right? Got it? And so now here these two resistors are in parallel, and so the effective resistance will be 50, you will get 100 by 2, and that 50 ohms is in series with this, right? Then 150 ohms you will get. So that means now this circuit R effective value I can write this as R effective is equal to 150 ohms. And therefore this current passing through the circuit we can write that as 6 by 150. So 6 by 150 means 1 by 25. So which is nothing but I can write 0.04 amperes. So this is nothing but now current passing through this. So which is nothing but the reading of this ammeter. So current passing here is 0.04. So that is the reading of this ammeter. And so now here that current will pass here, and actually that current will divide equally here I by 2 and I by 2. And again here this current will flow like this. This I by 2 current will flow like this. I by 2 current, here again this current is I by 2. Then so that the total current in this 100 ohms is high, because this voltmeter is an ideal voltmeter. So no current flows along this path here. The total current should flow like this only, right? Now the reading of that voltmeter we can write this as V is equal to I into R we can write, and so which is nothing but this 0.04 into that resistance is 100, and so that you can write this as 4 volts. So that is the potential difference across this. So that this will be the correct option for this. Reading of voltmeter is 4 volts and ammeter is 0.04, right? And so now similar to that of practical ammeter, this practical voltmeter should also have this error. And so now here also we can conclude that the reading of this voltmeter will be always less than the true value or the accurate value. That means from this we can remember it easily as the readings of measuring instruments like either ammeter or voltmeter will be less than the actual value only, because definitely practical ammeter or practical voltmeter will possess some resistance. So our requirement is ammeter should possess the high small resistance, very small resistance or negligible resistance. Voltmeter should possess a high resistance or infinite resistance. That is our requirement. So that means now here the practically then the readings of, that means ammeter will possess some resistance and voltmeter possess some resistance which is not infinite, and so that then their readings will be always less than this practical accurate values. So reading of either ammeter or voltmeter will be less than their accurate values. Now here let us see this. We are going to calculate the error in this. Suppose some current I is passing through the resistance R, so that its potential difference across this is V is equal to IR, we can write. Now to measure this value, this accurate value now, actual value, to measure this value, now we are connecting an voltmeter in parallel with this resistance, and we are taking this resistance of this voltmeter as R by V, right? Sorry, RV we are taking as the resistance of this voltmeter. And so now let us say this. And here again they are writing it as G by R, so don't note that G by R itself. We will discuss that how it is G by R later. In the conversions we will discuss that. Just let us take it as some resistance RV. And so now here it is connected in across this value here. Now these two are in parallel, we can say. And so now from this we can write this potential difference across this, we can write this as V dash is equal to I into, here this is nothing but we are writing it as I into R effective we are writing here. And as these two are in parallel, you can say that potential difference across these two will be same only, right? And so now here what we are writing is this I is equal to, means this V dash is equal to, what we are writing is V dash is the reading of this or potential difference across this voltmeter. So what we are writing is I into R effective we are writing here. So effective means the effective resistance of this small r and RV. So which is nothing but small r into RV by small r plus RV. And so now on simplifying this, you will get an expression like this. V dash is equal to IR by 1 plus R plus 1 plus R by RV. And so now from this expression also you can conclude that V dash value will be less than V, or V dash will be equal to V only when this RV value is infinite. And now again percentage change means V minus V dash by V into 100. So this will be our percentage change in that voltmeter, reading of the voltmeters. Then you can substitute this V dash and V values here. So then you will get this expression here. That means V minus V is nothing but IR, minus V dash is nothing but this expression you can substitute there. And so now from this you will get 1 by 1 plus R by RV you will get. And so now this is nothing but our percentage error here. They will give the R value resistance across which we are finding the potential difference, and they will give the resistance of this voltmeter. So from those two values you can calculate this percentage error here, right? And so next here, here let us say this, if suppose this voltmeter is having some resistance here. So let us see how to find this reading of this voltmeter. So now it is not the practical. We solved already one problem for this ideal case. Now let us see this case for the practical case. And so now this is the see the circuit here. The electrical circuit shown in the figure, calculate the potential difference across 400 ohms, that means this ohms, as will be measured by a voltmeter of resistance 400 ohms, either by using Kirchhoff law or otherwise. That means now we need to measure the potential difference across this 400 ohms. So for that what we are using is, we are using a voltmeter. Now this voltmeter is having some resistance. Now we can observe that a resistance of this voltmeter is given. So if the voltmeter is having some resistance, they will mention the resistance of that voltmeter like this, or sometimes they will mention in the diagram itself, right? So then you can treat that as a practical. If nothing is mentioned about that, you can treat that voltmeter as an ideal voltmeter. And so now, as we discussed in the previous cases, we need to find the effective resistance here. So when you are taking this effective resistance, then potential difference across that effective resistance is nothing but the reading of this voltmeter. And so now let us see this. So now here 400 ohms and this 400 ohms. That this 400 ohms means the resistance of this voltmeter, and this 400 ohms both are in parallel. So that here this resistance you will get this as 200. 400 by 2, 200 ohms you will get. So this circuit we are drawing like this. Now if you observe this carefully, now this is nothing but our Wheatstone bridge. So this is PQRS. That means this is our PQRS values here. So this is, you can treat this as PQ, and this value you can take it as R, and this is S. So this is the position of our galvanometer here, right? We solved already such a type of circuits there. And so that means clearly we are drawing like this. So PQRS. And clearly it is a balanced Wheatstone bit. So P by Q is equal to 1 by 2 and R by S is also 1 by 2 you will get. So that we can eliminate this resistance here. And so now here this is our circuit here, right? That means 100 and 200, 100 and 200. They are across this 10 volts. And so now our aim is to find the potential difference across this 400, which is nothing but this 200, or we can say this 200. We need to now find the potential difference across this 200. That is our reading of this voltmeter here. And so now from this effective resistance we are writing here, that is 300 by 2, because 300 and 300 both are in parallel. So you will get that as 300 by 2, 150. And so that this total current we are writing as 1 by 15. And as both the currents or resistors are 300 and 300, this current will divide equally. So half of this will pass through the each row. And so then this current passing through this resistance, we can write this as current passing through this resistance we can write as 1 by 30. And from this we can write this as potential difference across this 200 ohms as V is equal to IR formula we can write. So R is 200 and I is 1 by 30. So from this we can write 20 by 30 is the potential difference across that, right? So it is a potential difference across this voltmeter, or which is the reading of this voltmeter here. The galvanometer into ammeter. So just now we discussed about the galvanometer, ammeter and voltmeter. Now let us see how to convert a galvanometer into ammeter. So galvanometer can be converted into ammeter and can be converted into voltmeter. Just we are converting the galvanometer into voltmeter. Ammeter means we need to increase the range, because galvanometer already measures the current only, but it's very small current. Now we need to increase the range of this galvanometer, right? So then for this we can use this procedure like this. So conversion of this galvanometer. So this galvanometer is generally used to measure the small currents here, and it also measures the direction of the current as shown here. So it can be measured the direction of the current of this galvanometer. If current is flowing in one direction, it will show the deflection in one direction. If current is flowing in opposite direction, then it shows the deflection in the opposite direction also. Now it can be converted into ammeter just by connecting a very small resistance in parallel with this galvanometer. So we are connecting a small resistance in parallel with this galvanometer. This small resistance is nothing but we call the shunt resistance. So the small resistance connected in parallel with the galvanometer is called shunt resistance. We connect a very low resistance. And so now as we are connecting the low resistance, very small current will flow through the galvanometer, and a large amount of current will flow through this low resistance here, because the resistance is low means then more current will flow through the shunt resistance there, right? And so that we can allow the large current in the circuit here. So that means now here current I is entering the circuit, and this is the current to be measured, and out of this Ig is the current flowing through the galvanometer, and which is the maximum current. This Ig is nothing but we call the maximum current or full scale deflection current. And next to this I minus Ig is the remaining current flowing through the shunt resistance here, right? Now this galvanometer resistance is nothing but we take it as G, and this shunt resistance we are representing as a S. And now this I is the total resistance, total current flowing through this galvanometer, total current flowing through the ammeter. Now this I minus Ig is the current flowing through the shunt resistance, or we can represent this as with Ic. And now these two are in parallel here. As those two are in parallel, the potential difference across them should be same. And so that here potential difference is nothing but Ig into G. That should be equal to the potential difference across this I minus Ig into S. And so from that we can calculate this S value as Ig into, from this we can calculate this S value as So from this I can write this S value like this. The shunt resistance we can write this as so this is the shunt resistance here. S is equal to G into I by Ig by I minus Ig, or generally we can express this value as S into, we express like this. Note down this form, G by, here Ig I can take common, so that we can express this as I by Ig minus 1. So then this form will be more useful for us, because this Ic, if you are writing in this form, then you can do the calculations easily. So try to write in this form here. S is equal to G by I by Ig minus 1. So where I is the maximum, that means the range of this ammeter. Now this total circuit, this total part is nothing but we called ammeter here. So this is our ammeter here. This galvanometer plus the small resistance connected in parallel. That part is nothing but we call the ammeter. So this arrangement will act as an ammeter here. Now the range of this ammeter is nothing but this I here. I is the range of this ammeter, right? And so now this Ig is a full scale deflection current here. Full scale deflection current, or it is said to be the maximum current that can be measured by this galvanometer here. And this Ig, this is nothing but sometimes they may ask about the shunt resistance, current passing through the shunt resistance here. So we represent with the Is value here, right? So that Is value is nothing but I minus Ig, and this S is the shunt resistance, which is generally our required value here. And so now the value of this shunt resistance will depend on this I value, how much current we need to measure. So that means this current is nothing but current to be measured by using this given ammeter, or the maximum current, the range of current. Like for example, if you are converting this galvanometer into a range of 0 to 10 amperes, right? Now this 10 amperes we need to take this as I. If you are converting from 0 to 5 milliamperes, for example, now this 5 milliamperes we need to take that as I. That means that is the range of the ammeter, we can say that. Range of the ammeter. So that is our I value. And Ig is the full scale deflection current, G is the internal resistance of this galvanometer. So then S is the shunt resistance, right? That is S is the shunt resistance of this galvanometer here. Shunt resistance to be connected in parallel with this galvanometer there. And so now the resistance of this ammeter means now we need to find the these two are in parallel here. G and S are in parallel. So the effective resistance of this ammeter, and previously in the previous discussion there one term is there, A is equal to G into S by G plus S. Now that is nothing but these two values here. And so that we can write this value as 1 by Ra is equal to 1 by G plus 1 by S, which you can write that as Ra is equal to G into S by G plus S, we can write there. So it is a conversion of this galvanometer ammeter into the galvanometer into the ammeter, right? Now so this arrangement will act as a now ammeter here. So this is our ammeter here. This blinking part is nothing but the total arrangement is nothing but we call that as an ammeter now, right? Got it? And so now here that we can note like this. And so now here you can note this part here. Just we are converting this ammeter and galvanometer like this. So galvanometer and a shunt resistance is connected in parallel here. A small resistance is called shunt resistance here. So you need to remember this. So then I and Ig, and this is I minus Ig, and from this we are writing here, and note this expression for this. And so note again, as I said, note this S value as in this form here. So that this S is equal to G by I by Ig minus 1, right? So generally for the shunt resistance, if you are remembering this form, you can solve the problems easily. So that is the shunt resistance, and the resistance of this ammeter is nothing but, as I said, the resistance of this ammeter is nothing but the total resistance of this ammeter is nothing but now G into S by G plus S. So this is the total resistance of this ammeter. And here don't confuse here. Ammeter is to be connected in series with the circuit. That is the first point we discussed there. Now to convert the galvanometer into ammeter, a small resistance must be connected in parallel. You need to remember this point. A small resistance to be connected in parallel. Generally, galvanometer will have the high resistance of order 100 ohms or 50 ohms or 150 ohms. That range will be like that. Now if you are connecting directly the galvanometer in series with the circuit, so then current in that circuit will changes by large amount. And so now we should reduce the current there. We are increasing the range of the galvanometer, means we are reducing the effective resistance also. So then we know when two resistors are connected, that means now the shunt resistance will be like 0.001 ohm like this. Now the 0.001 ohm and the resistance of the galvanometer is 100 ohms, for example. Now this effective resistance, we can write this value as definitely it should be less than this 0.001 ohm we can write. Now see this, from 100 ohms now we are reducing the resistance of device from 100 ohms to less than the 0.001 ohm we are reducing there, right? So that is the advantage of connecting the small resistance in parallel. So that means the resistance of the device will decrease by the large amount. And how much resistance we need to we need to connect in parallel means that depends on this current here, how much current you want to measure. So then based on that we need to connect suitable resistance there. And actually if you are connecting this shunt resistance in parallel with this, the sensitivity of this device will changes there. The sensitivity of this device decreases there. And so we will discuss how it decreases. A numerical problem is there that will decrease, we will discuss there, right? And so now here directly, just if you are connecting as is shown in the video, if you are connecting directly a resistance in parallel, directly it won't become ammeter. We need to calibrate the scale also, because previously it was in microamperes, and so similarly now we need to convert, we need to calibrate that. Now previously suppose say one division, each division on the scale represent 1 microamperes there, right? Now it may represent 1 milliampere now, or it may represent like 0.5 milliamperes, or the one division value may represent like 2 milliamperes. So whether it represent 1 milliampere or 2 milliampere, according to the given resistance or according to the given range, calibration needs to be made. So that means the same device now will measures the current in either milliamperes, or it depends on the range, it may measure the current in the amperes directly there, right? So from microamperes to, we may increase from milliamperes, or we are increasing from this microamperes to amperes. So this will depend on that means this process has to be done. So then that is nothing but we call calibration. So calibration means, like simply I can say that if you are measuring the temperature by using a thermometer. So in thermometer actually what we will measure there, we are measuring the temperature directly. We are noting the temperature just by keeping the thermometer. We are noting the temperature directly there, as usual mercury thermometer, right? But actually what we are measuring actually there is increase in the length of this mercury column. So there you know this mercury column will be there, small capillary tube will be there. In that small capillary tube this mercury level is increasing here, right? So we are measuring this level of this mercury column here. That means actually what we are measuring there is length we are measuring here. So that length is calibrated. Now the scale is calibrated into temperature, either Fahrenheit or centigrade. We can calibrate this. That means one division here will represent 1 degree Fahrenheit, or like 2 degree Fahrenheit. So that is nothing but now we call calibration here. Similarly here the calibration is to be done for this scale here. We are connecting a resistance and we need to do the calibration for that scale also. Then directly we can note the required current by using this ammeter there, right? So it is a ammeter conversion. So regarding this you need to remember that a galvanometer can be converted into ammeter. The important points now I am saying here. Converted by connecting a very small resistance known as shunt resistance, or simply we can call it as a shunt, in parallel with it. Again I am saying ammeter is always connected in series with the circuit if you want to measure current in any branch of the circuit. But for the conversion you should remember we need to connect a small resistance in parallel with the galvanometer so that it becomes a ammeter. Now the resistance of this ammeter, that means shunt resistance, how much resistance we need to connect means we need to remember this, G by I by Ig minus 1. So this is the formula for this shunt resistance here. And the total effective resistance of this ammeter is nothing but now this expression here. This is the total resistance of this ammeter, right? So that is a conversion from galvanometer to ammeter. And here there may be sometimes there may be situations like already they will give the ammeter and we need to increase the range of this ammeter, and so then already they are giving some ammeter, we are increasing the range of this ammeter. Suppose here it is already that ammeter will measures from 0 to 5 milliamperes. Now we need to increase its range from 0 to 100 milliamperes for example. That means here maximum current it can measure is only 5. Now we need to increase its range from 0 to 100 up to 100 milliamperes we need to increase here. So it is already ammeter only, just we are increasing the range of the ammeter. So now it is exactly we can consider it as a conversion of galvanometer into ammeter. So whatever the initial ammeter given, that you can treat that as a galvanometer. Got it? Whatever the ammeter it is initially given, you can treat that as a galvanometer, and we can apply the same formula as that of the conversion of galvanometer into ammeter formula. Got it? So this initial device, whatever the initial device given here, that you need to take it as a galvanometer, and whatever the final ammeter range we want to get, that we need to convert it as, that means we need to consider it as our ammeter. So just we need to convert from ammeter 1 to ammeter 2 as conversion of galvanometer into ammeter. So this is the shunt is the required resistance here. Now suppose A1 is the resistance of ammeter and A2 is the resistance of, that means A2 is our final reading here. And so now this shunt resistance, for this we can write now this as A1 by I by Ig minus 1. Now this Ig means, for example, in this case 5 milliamperes we need to consider. I means 100 milliamperes we need to consider. Ig is 5 milliamperes we need to consider. Now this Ig means, in this case Ig means the maximum current that can be measured by this given ammeter. If here, for example, if I1 is given here, so let us apply this formula only, just to write the meaning there. That means to convert this, we need to use the same formula here. I am writing the same formula here, I by Ig minus 1, right? Now here G means, the G is the resistance of the given ammeter, and Ig is the maximum current that can be measured by this ammeter, and I is the maximum current required here, maximum range of the ammeter required here. So then by using the same formula, you can calculate this shunt resistance required there. So it is a conversion of this ammeter from one ammeter to another ammeter. That means just by increasing the range. And next, similarly, let us see the conversion of this galvanometer into voltmeter here, right? So just a minute. Now see how to convert this galvanometer into voltmeter. Now we are going to discuss about conversion of the galvanometer into voltmeter here, right? Now see this. So galvanometer conversion, galvanometer into voltmeter here. So as we discussed already, voltmeter means it should possess a very high resistance here. So it should possess the very high resistance. The resistance of the voltmeter should be as high as possible, and practically it should possess this ideally it should possess infinite resistance. Now this is the high resistance we need to connect here. High resistance we need to connect in series. We need to connect the high resistance in series, because so that the resistance will increase by the large amount here. Our requirement is it should possess the very high resistance. So that high resistance is connected in this series here, series with the galvanometer. And how much resistance we need to connect here, that depends on whatever the range of the voltmeter required. That means whether you want to measure 0 to 10 volts or 0 to 5 volts. So that depends on that. And so now here, so this is the galvanometer here. The galvanometer resistance is again G we are taking here. R is the resistance, high resistance connected here. R is a high resistance connected here. And so now here by using this we are connecting, we are measuring a potential difference of V here. So by using this arrangement, we are measuring a potential difference of V here. So that is the range of the voltmeter. This V is the range of the voltmeter. Now we can observe that as this Ig is the current, maximum current flowing through the galvanometer. Now the same current will flow through the resistance also. Through this resistance also now same current will flow here, right? And so now this by using this total potential difference across this combination, we can write this as that should be equal to the required potential difference here. The total potential difference across this combination here, across this G and R. So that can be written as Ig is equal to V by, if V is the potential difference here across this combination, V by R plus G we can write. Or from this we can write this R value as our R is our required value here. So from this we can write R is equal to V by Ig minus R we can write. Got it? V by Ig minus R. Ig minus G. So R is equal to V by so say this so now say this V by I minus G. So this just we are writing, or you can also write like this. You can also write this value as like the potential difference across this, we can write this as V is equal to Ig into R plus G we can write. The potential difference across this combination, right? And so from this I can write this value as R is equal to V by Ig minus G. Simply you can remember like this. So the potential difference measured to be equal to Ig into G plus R into Ig we can write. So that should be equal to the potential difference to be measured here. So from this we are calculating this R is equal to how much resistance we should connect in series, means by using this formula now we can calculate that resistance required there. So right, and so now here now automatically as we are connecting this resistance in series here, automatically the resistance of this circuit will also increase here. Now the resistance of this total voltmeter means we need to write like plus R. So G plus R is the resistance of this voltmeter here. So RV we are taking that as the resistance of voltmeter. Now this total combination will behaves like a voltmeter, as I said in the previous ammeter. So now here this is the total combination will behaves like a voltmeter here, right? So that means now this voltmeter should possess a very high resistance here. Resistance of voltmeter should be very large as compared to the resistance across which voltmeter is connected, so that it measures the accuracy of this voltmeter value will increase there. Got it? So that is a conversion of this voltmeter galvanometer into voltmeter here. So for conversion, so you can revise here, we need to convert this, we need to connect a high resistance in series with the voltmeter. But in the circuit, how the resistance is connected, how this voltmeter is connected, voltmeter is connected in parallel with the circuit. Where you want to measure the potential difference across that resistance, we connect the voltmeter in parallel. But for the conversion of galvanometer into voltmeter, a high resistance should be connected in series here. So if it is not possessing high resistance, what will happen? We already discussed there. That means here that is nothing but what I am mentioning here. If you are drawing some, that means if it is not having the required resistance, large resistance, it draws a part of the current from this main circuit, and so that the current in the main circuit decreases, automatically the potential difference across that circuit will decrease then, right? And so now here this is the we can represent that circuit like this. That conversion here again I am representing like this. So this is our required value here. So then galvanometer and this resistance both are connected in series here, high resistance. So then G plus R into Ig must be equal to the potential difference across this combination, which is the maximum range of this voltmeter there. So then from this we are calculating this R value like this. And again if you want to convert one voltmeter into another voltmeter, like our previous ammeter into another ammeter, again we need to take this initial one as a galvanometer. This value we need to take it as a galvanometer, and this is the voltmeter we need to consider here. And so from this what we can write is our required resistance, what we can write is V by Ig minus G we need to write here. So where V is the range of this voltmeter and Ig is the maximum current that can be measured by this voltmeter, and G is the internal resistance of that voltmeter. So just here previously we say for this G means internal resistance of the galvanometer. Here we need to say that this we need to consider as a galvanometer, and so it is the resistance of the voltmeter we need to say here, and this is the range of this voltmeter. That means here in terms of V1, V2, if you want to write V2 value, we need to substitute here V2 by L. That means the range of the final voltmeter, resulting voltmeter we need to write here. And so based on this, direct simple problems will be there, so you can solve those problems easily here. So like for example, here I am taking one example here, a galvanometer having the coil of resistance 100 ohms gives a full scale deflection when current of 1 milliampere is passed through it. What is the value of resistance which converts the galvanometer into ammeter, giving a full scale deflection current of 10 amperes. So that means now here from 1 milliamperes to the resistance of the maximum range of the galvanometer is 1 milliampere. So that is our Ig value. So here we can write this Ig is equal to 1 milliampere. Now I value is we need to increase its range to 10 amperes. And resistance of this galvanometer is 100. So our formula is G by I by Ig minus 1. So you can simply apply this formula and you can simplify this. So that this value is 100 by I is 10 by 10 power minus 3, 1 milli minus 1. And so that this value you can write this as 100 by 10 power minus 10 power plus 4 minus 1. So sometimes they may give this value like this 1 is negligible, they will give, that depends on the options there. The further simplification will depends on the options. Now when compared to this 10 power plus 4, this 1 is negligible. So you can write this value as 100 by, you can take this value as approximately 100 by 10 power 4 you can consider, or S value is nothing but 10 power minus 2 ohms we can consider here. That means you can observe this, we are connecting a small resistance here, 0.01 ohm. And you should also remember how it should be connected to convert the galvanometer into ammeter. This small resistance should be connected in parallel with the galvanometer. So this amount of resistance should be connected in parallel with the galvanometer. And whereas similarly, so the next problem based on this, a galvanometer having the resistance coil 100 ohms gives a full scale deflection current when a current of 1 milliampere is passed through it. What is the value of resistance which can be converted into convert this galvanometer into voltmeter, giving a full scale deflection for a potential of 10 volts. So here Ig value is again 1 milliampere. Now the V value is 10 and resistance of this galvanometer is 100. So again our formula is for resistance R is equal to V by Ig minus G. So here V value is 10 and Ig value is 10 power minus 3 milliampere minus this G value is 100, right? And so that this value you can write this as 10 power 4 minus 100. So it is 9900 we can write ohms. So which is nothing but we can express this as 9.9 kilo ohms. So that is the resistance. Now how this resistance should be connected? This high resistance must be connected in series with the galvanometer, so that it converts into the voltmeter. So up to now what we discussed is conversion of galvanometer into ammeter and conversion of galvanometer into voltmeter. And here again don't confuse with that. Ammeter is always connected in series with the circuit. Voltmeter is always connected in parallel with the circuit. But for converting galvanometer into ammeter, a small resistance must be connected in parallel. But to convert a galvanometer into voltmeter, a very high resistance must be connected in series to convert the galvanometer into voltmeter. And so then that is a process of conversion here. And these are the expressions how much resistance we need to connect either in series or parallel to convert into ammeter or voltmeter, right? So that is a conversion here. And another important thing is the practical, that means the ideal ammeter should possess a zero resistance, and practical it should have very low resistance, and ideal voltmeter resistance is very high. So the ideal means it should be zero, and practical it should have very high value. and why it should possess that ammeter should possess 0 or ideal voltmeter should possess infinity also we discussed it there. So that means ammeter, if it is having high resistance, then total resistance in the circuit will changes by the large amount, and so that current will decrease, and so that it does not give the actual value. And similarly, if voltmeter is having, if it is not having the infinite resistance, then it will draw a part of current from the main circuit, so that current passing through the main circuit will decrease, right? And so that it does not give the accurate values there. So that is a conversion process. And in the next class we will discuss some more problems based on these conversions here. These conversions are important, as I said in the previously. This total meters part is very important for the advanced point of view or for the mains point of view. Many questions, previous questions are there based on this, right? So then try to solve the simple problems based like this, direct formula substitution based on the conversions. And I will explain some more problems based on these conversions in the next class, right? Thank you.